You very much for turning up my talk. It's almost full house. It's pretty amazing. Thank you very much again. I would like to start my talk with a quote from 18th century Prussian general and military theorist von Clausewitz. Machine learning is the continuation of software engineering by other means. We are going to see in this presentation that we can borrow a lot from software engineering applied to machine learning to make ourselves more productive. The title of my talk is Clean Architecture, How to Structure Your ML Projects to Reduce Technical Debt. First of all, we are going to see how technical debt ruins your productivity. We will look at why machine learning products are particularly prone to collect technical debt, and a couple of relevant software engineering concepts like decoupling, refactoring, and design patterns to help yourself avoid this. About me. Why is this like this? About me. About my past, I have a finance background, mobile gaming, and I was head of data science at a London fintech startup. Now I teach data scientists to write better code. Also, I am a startup consultant. Please check out my blog at laszlo.substack.com. What do we mean by ML products? It's important to, sorry for, why is it, shall I give it a try? Okay. Cool, sorry. I was just mixed up. So let's look at what do we mean by ML products. It's important to understand that MLOps is not ML products. MLOps is an infrastructure that you are using to facilitate ML products. And it's also not data analysis. Data analysis have a fixed starting point when you are gathering the data, and then it has a relatively short period of lifetime when you are handing back your results to the stakeholders. Even that applies if you're using machine learning techniques in advanced analytics situation that still not create an ML product. ML products are complex business processes that are usually described by input-output relationships end-to-end, and they work usually autonomously. They don't require particular amount of manual work to facilitate the operation, and they usually have a long lifespan. And one of the reasons why dealing with technical debt, refactoring, investing into quality code is a high-yield activity, because you can yield this back over a long period of time over the entire life cycle of this ML product. Why does technical debt matter? ML products usually solve complicated business processes that are very fuzzy in nature. They're not described by rules. They are described by edge cases and ad hoc rule of thumbs. And this is why usually rule-based systems are not a good baseline for machine learning products. They are also inherently unspecifiable. It means that no matter how careful you are specifying your ML product, there is going to be aspects of the work and features that you are going to find out about while your product is in production. Why? Because of the fuzzy nature of every business process. You know, if it would be easy to specify, you can write rules, and these rules would solve your problem. And not only that, but also they need continuous updates. You know, the context they are operating changes, the environment, the business needs are changing. You know, this is particularly important in data drift. So you need to, by definition, prepare for change. And changing creates technical debt. Let's take a look at ML lifecycle and how that impacts data tech debt in machine learning products. Classically, there is 5 steps of an ML lifecycle. You have EDA, like exploratory data analysis, when you are concerned about the data, proof of concept, when you are concerned about the models, In the MVP stage, you are doing productionization and fine-tuning in A/B testing, and classically you think of business as usual as an important place for monitoring. So why this is not a particularly good structure? Often the first two steps are not even done by the same people than the rest. You know, the first two steps are done by data scientists, and then from the productionization is done by machine learning engineers. The translation between them creates a friction that is slowing down the iteration speed. When you are analyzing A/B tests, you know, these are necessarily fed back to the early stages because only the data scientists are able to collate this knowledge into one place. They need to take this knowledge and update the machine learning engineers to update the project. This is a high friction technique, which is unable to run at a high speed iteration, which means that changes can accumulate before they are translated into production, which means that two steps of the same version will going to go further away from each other. And that means that sooner or later, each version update will going to be a big deal. It can create business continuity problems, so it means that you need to plan for it, and it's even longer. And often what you see in machine learning products is instead of setting up a continuous integration or a continuous update pipeline, rather they just scratch the previous version and then write a new one from scratch. You know, this is clearly not an agile way of solving problem, which we know that it is fuzzy in nature and changing as we go along. What's the difference between technical debt and technical mess? It's a specific term for what you sometimes experience. It's important that lack of specification, documentation, and infrastructure is not technical debt. You are just haven't finished particular aspects of your work. It's also not missing features. You know, if you are missing something, you just need to add it. You don't address that as technical debt. And it's also not broken models. If your model is drifting, you know, you just need to update it, and that's the right term for that. It is drifted. And most importantly, it is not bad practice. Technical debt and referring to certain practices as creating technical debt is not a license to create bad practice. And it's a very important term to use technical mess for these expressions, because otherwise the technical debt would give you a license to get away for doing technical mess. So what is technical debt? Technical debt is an attempt to gain knowledge with a plan to correct it later. Just like when you are getting into debt, and here I would refer to corporate debt, not credit card debt. Credit card debt is always a bad idea, but corporate debt is a natural way of facilitating a business if you have a plan to pay it back. You know, if you don't have a plan to pay it back, then it's just recklessness. You know, you're just not a prudent way to run a business. Ward Cunningham, who coined the phrase technical debt, said that paying back tech debt depends on writing code clean enough to be refactored. And let's take a look at what refactoring means. Refactoring means changing the code without changing its behavior. Why would you do that? Why would you change the code without changing its behavior? We know that everything can be solved multiple ways in computer science. Why do you think that the first solution is the best solution that you can come up with? So often the way you solve problems in computer science is that first you solve this problem and then you transfer this solution in a way that can enable the solution of future problems and the maintainability. And this is exactly the purpose of refactoring, is turning an existing code, an existing solution, into something which is nicer. It requires two steps. It needs fast testing. It means that you need to have an easy way to verify that the change, what you did just to the code, didn't break that code. And it also requires what's called experimental operational symmetry, EOS for short, which we are going to see why is it important. So what is EOS? It's Google's fancy name for running the same code everywhere. This is, you can see that in the traditional machine learning lifecycle, when the data scientist and the machine learning engineer is not using the same code, this is the principle that is broken. This enables refactoring. So the same code, where do you run the same code? You run it on your laptop. You run it in testing, training, evaluation, and production. But it's always the same code, and it requires two things. So it enables refactoring, but it requires something called decoupling. What is decoupling? Clearly, on your laptop, you don't have the same resources as in a cloud infrastructure or a distributed architecture, so somehow needs to be able to run this code without certain features existing. And decoupling is the paradigm to reduce the dependency between components of your architecture. It allows you to, with interfaces, to hide implementation details of the peripherals. So these peripherals can change without impacting the core of your problem. And this also helps you to break cake, which is changing anything changes everything, which is a particularly prone problem for machine learning. How do you achieve this decoupling? You can imagine your machine learning product is defined as a class. This is what you see in the blue box. And it requires two decoupling steps. One, first is inversion of control. The second one is dependency injection. What is inversion of control? Traditionally, when you write a code, you think of your code as running, and it calls infrastructure services. This is the direct control. Inversion of control tells you that the infrastructure calls, instantiates your product as a class, and then calls the main entry point. And this is what you see in the image. Why is it good? Because it means that the running code is not aware of whether it runs in an infrastructure or in a test infrastructure, and therefore you achieve decoupling from wherever you run the code. You also decouple with dependency injection from external interfaces for databases or external services. This happens through adapter classes, and we are going to see a couple of examples later in the talk. So in the test environment, you are using the same code. You are instantiated in the test harness and call the main entry point by the test setup, and replace the adapters with connections that connect to temporary services that allows you to verify whether your code did the same thing as it would have done in production, and passes the test setups. Inside your code, how do you structure? Every kind of machine learning product has some kind of business problem at its center. This is why I drew into the bullseye the business problem. This is surrounded by business-specific terminology, domain model. So, for example, if you deal with customers, you have a customer class. If you deal with transactions, then you have a transaction class, or anything that is using the same language as your business uses. It means that at this point, you can communicate with this without translation. If you have data frames and column names and SQL queries, it's much harder to talk to a subject matter expert if you don't use the same language. And obviously, this is true for the business languages. This is surrounded by the machine learning specific techniques like data sets or training or evaluation. And only this outer layer is connected to the infrastructure, which is like databases or computing infrastructure. This have the additional benefit of outsourcing these to other teams and cooperating with other technical teams at the company, because obviously these are decoupled from your main problem, so it means that you can just outsource them and they can work with you much more efficiently, while you can focus all your attention to the center, to the actual machine learning product. That is where you are adding most of the value. How does it happen when you see the previous images? You see moving from the infrastructure to the test structure. Here you can see the same thing in clean architecture. How do you swap the out-test layer to temporary structures that enables to run the same code in a much smaller place and still do it efficiently? How do we actually implement that? So we are going to look at 3 simple design patterns, which is essentially doing the same thing. How do you handle dependency injection for 3 particular states? The adapter pattern, which you have already seen, allows you to decouple from external services. The factory pattern allows you to decouple from data sources, and the strategy pattern allows you to decouple yourself from algorithmic decisions, which is particularly important in machine learning because usually you try to experiment with different algorithmic decisions, and you still need to maintain some kind of coherence in your solutions and don't need to rewrite your entire code base for every problem you do. So let's take a look at the code. Is it visible? Can you read it? Okay. So you can see that the code has already been refactored into a class, and the infrastructure, which is now a shell script, instantiates this class and calls the main entry point. So you can see that inversion of control is already implemented. So what does this code do? It creates a database connection and then goes to that database, run an SQL query, and get the data into a data frame. What's the problem with this? Obviously, if you're running it locally on your machine and you don't have access to this database, that this code will not going to run. If you change this code, you have no idea whether you didn't break it. So what you can do, clearly the problem is that the main function is aware of the existence of a database that may or may not be present. So essentially, you move all of the code into a separate class, which is named SQL source. And the main class only knows the existence of a source which has an interface called getData, and this getData will going to give you that data frame. But the main program doesn't know where is this data coming from. And you can see that now the infrastructure instantiates the main program with this source. And if you want to run it in a test structure, you can replace only this SQL source with a, let's say, a file-based class and do the same thing and run it again. The next one is a factory pattern. So we see in the previous query that the query is concerned about customers, but instead of a customer, you are getting back a data frame, which is not a domain-specific class. So what would you do? Let's do another refactoring step when instead of a nondescript technical implementation like a pandas data frame, you are getting back domain-specific classes, and the rest of your code can depend on something which is the same as you talk to the subject matter experts. And you can see that in the last line, you are using the same instantiation. Instead of the SQL database, you are instantiating a domain-specific data source. Let's take a look at the last pattern. What I'm going to talk about is a strategy pattern, which is classic problem that happens in a lot of machine learning products. It is the same situation. A customer class is transformed into features, and that's fed to a logistic regression, which creates a prediction. What's the problem with this? Is that obviously if you would like to replace and use a different model and do an experiment, you need to rewrite your main code. This can be entangled several places, which means that anytime you change the code, you are risking that you are going to break something. You would like to have this version running and another version with a different model running at the same time as well, and make sure that you change the less amount of. What you can do is you can move all of this code into a specific function. Strategy pattern is just an externalization of an algorithmic dependency, and you can see that the main code now only deals with a model predict interface. It doesn't know what kind of model it was calling. It means that you can replace with whatever model you want. If you want to have random forests, you can instantiate that here. Down, you need to write another class, and your main program will going to run in the same way if they have the same interface. Right? This is one of the most used design patterns in machine learning applications. The strategy pattern also have another important driving force, which is called coherence. Essentially, let's say on the left-hand side, you can see that here is a deep model which has layers, and obviously in instantiation, I specify that I need 5 layers for this model. This information that it has 5 layers is put into the constructor and then passed onto in the main function to instantiate a model with 5 layers. What's the problem here? If you would like to use a different type of model that doesn't have layers, what do you need to do? You need to rewrite every place where I was specifying these layers. Instead, if you use a strategy pattern, you externalize this information. In the construction, you are only passing this information to the model itself, and the main code is not aware of what kind of model it is running, and the code is more compact, and it is at the place where it is supposed to be. If you replace this model to, let's say, use random forest, which has a number of trees as a parameter, you don't need to change your main code again, while at the same time you are maintaining the old version as well, because obviously this is just one line to change this. So how does a general workflow look when you start from scratch? Usually, you define your data classes based on the specification. This is usually coming out when you are talking to subject matter experts of what kind of problems your machine learning product needs to solve. And then you wrap your data sources with the factories that are creating these data classes. And you only deal with these data classes in the rest of your machine learning product. Then you set up a test environment. One of the fastest way to do that is to create functional tests with like a small amount of the data, what you need to use. You run your entire pipeline with 0.1% of the data sets, or whatever you think that is enough to ensure that the change of the code is safe. Then you define your interfaces. These are usually the verbs. So the data classes are usually the nouns. The verbs are, do or get or create or all of this. And then collect these interfaces into service classes. If you are thinking about your product, let's say a microservices architecture, then these service classes is like the proto-abstraction of a service that is going to be a standalone program in the future or not. You don't know whether refactoring will going to eliminate some of these services. Once you have done that, then you can start dependency injection with, like, you structure your code, you move the right places to the, usually you collect quite a considerable amount of technical debt on this, because this is the first part is a very evolutionary step. So the structuring and the dependency injection will going to help you to increase the coherence and create optionality for you to go to production. Then you wrap your external services with adapters, doing the same interface that you were using previously with in the test environment, and then you can set up the production environment, namely instantiating your product with the adapters that connects you to the real world. And then you can create experiments with the strategy pattern, because that's what it is purpose, that without destroying the production environment, you can create other contexts where you can run these experiments and solve these problems. Obviously, most of you work in notebooks like us. So how does this work in a notebook environment? We usually load, because the factories are classes themselves. You can instantiate them and get the data. They get the data classes in notebooks. And then we turn these data classes into data frames and do any kind of analysis on that. And then the other thing what you can do is you can create custom experiments by instantiating main program. The main program itself is a class which you can create inside your notebook. And then you can create experiments in your notebook with the strategy pattern to a certain extent, obviously, dependent on where your notebook server is running. What are the benefits? We found that there is good layers of abstraction in this structure. You have one place where you do analysis in notebooks. You have one place where you are writing your production code, which is in VS Code. And then you can outsource a lot of the infrastructure problems or allocate time box time for dealing with how do you write adapters and what do you do with them. But you can externalize these problems. It gives you a high level of flexibility. You are able to change your code and back out of it. So that's a very important productivity tool in machine learning, where you usually do high-risk experiments, and you don't want to accidentally ruin your code. I'm sure everyone did it before. I did plenty of time when I regretted changing my code. And it also have managed complexity. We found that machine learning problems are inherently complex. You cannot have simple solutions. It's that they don't exist. You don't try simple solutions. You are managing complex solutions, and this allows you through the decoupling and the externalization of infrastructure problems, and it enables high-speed iteration because you have the same code running in every place. You have only one version of it. It means that when you change it and you know that it didn't break this change, and you have a cascade of test suits that we are going to validate that this is going to go into production and is not going to break anything, then you can reach high-speed iteration. So let's go through this again. So we see that machine learning is inherently unspecifiable. That makes technical debt inevitable, and you need refactoring to remove this technical debt. You can't have refactoring without testing and EOS. To have EOS, you need decoupling. To decouple, you can do it through clean architecture and inversion of control and dependency injection. And you can achieve this by 3 small design patterns called adapters, factory, and strategy. And thank you very much for your attention. This concludes my talk. Please subscribe to my blog. This was a very short amount of introduction to this concept, and I write regularly about it. Thank you very much.
Thank you very much, Laszlo. We've got some time for questions.
Given the high amount of data frame usage within more machine learning and I guess Python and data analysis in general, given these patterns as well, how do you feel about MyPy and typing to kind of conform to interfaces and make sure that, I don't know, say a technical person who's implementing, say, the adapters, that the person who's actually using them actually conforms to them and actually uses them? Because I didn't see any of that.
I didn't use typing. I would think, okay, so data scientists are a bit reluctant to care about their software engineering skills. I'm sure you experienced that. Or philosophy, like this is obviously an advocacy, an evangelism of this to data scientists, and we try to use the least amount of moving components to teach in one go. I would consider typing to be optional with the caveat of, obviously it's a corporate policy or an engineering policy, whether you demand it or not. And I do see usefulness in that, but I do think it is optional.
That makes sense.
And I do think that you should minimize your data frame usage outside of analytics.
Thank you for the talk. One consequence of dependency injection is now you need to manage the bootstrapping, just to provision all this, do the actual injection for your system. And I feel that you might be pushed the complexity to that part. And Python being a dynamic language, it can be really hard to achieve this because you might break something without you realize. You might break the specification, the interface, without you realize you have also broken the bootstrapping. How do you manage that?
Mm-hmm. Yes, very good question. I think you need to have testing. Managing complex systems is not going to be simpler just because we use one technique or another. You still need to write enough tests and usually deal with enough edge cases to resolve this problem. Did I answer the question?
It's more about it's more about the bootstrapping because if you go back to the slide of the example of the dependency injection,
yeah,
there's a part in the main logic to actually inject the object into it.
Yeah.
So potentially, because dependency can go really deep, right? Can be a long chain.
Yeah.
So how do you manage the complexity of that with
it's
Python?
Interesting. I don't know. Let's take this offline, right?
Hi, thank you. Great talk. I wanted to understand what you think about the usage of Jupyter notebooks and if you think that it's an anti-pattern in machine learning projects.
I would think that we found that it is usually there was just a talk before this who showed relatively a lot of infrastructure to manage notebooks in like a verified environment, and I think it's a sign that if you have all your relevant code in pure code, and then you just use notebooks for analysis, then it's a better pattern. And we only use data frames in notebooks for analytical reasons, but everything else is in domain-specific classes.
Thank you.
How do you deal with unit testing a machine learning algorithm which is inherently stochastic? For example, I've worked with data scientists who have written a unit test where they basically ran the algorithm, dumped the output of the resulting data frame, and then their test compares it, the next run, with that to 10 decimal places.
Yeah,
and that seems worse than no test at all.
That's what we do as well, yeah. Obviously, within reason, the goal here, we spent actually quite a lot of time on figuring out, and Kent Beck said that when he worked for Facebook, Facebook was not doing testing. And Kent Beck was like the original test-driven development guy, and then he had this kind of existential crisis of how is it possible that one of the most successful companies in the world doesn't follow his principles and still, thrives. And it means that if you can verify your code that it does what it did before after changing, then you are good. So find something to test, and this is what we do, running the entire pipeline on a small amount of data. So that's one problem. The second is machine learning. We found that the engineering style testing for statistical problems is just not feasible, and you always end up in some kind of analytical state where essentially you're running the entire pipeline and data scientists just stare at these numbers for days trying to figure out whether the latest change in a model was having the intended effect or not, and these are enough to verify that major breakpoints didn't happen. So that's our workflow in terms of testing. So this kind of small amount of data testing is literally just testing whether your code is not broken, because it will going to fail relatively easy.
Okay, so do you distinguish between not broken and not giving the right results?
Exactly. Because it's so difficult to specify. I mean, that's exactly why you're using a machine learning algorithm, because you have unit test would require relatively simple rules for defining your system through the specification, and that's the very nature why software engineers haven't solved this problem with software engineering techniques. That's why it ended up on your table.
Okay, thank you.
Hi, thanks for the talk. So my original question was regarding the factory pattern and how you replace the data frame with a customer class or whatever is domain relevant. And my question was, yes, but if we want to have a performant operation, we need to vectorize it. So effectively, whoever is going to operate on that customer, whatever abstraction is, has to have a vectorized operation, which is Panda specific. So we haven't really decoupled anything.
Yeah.
And I guess your answer now would be don't use pandas. So
I would
like one thing only. If your answer is don't use pandas, then my follow-up question is how can you justify losing that performance? Because like I did exactly what you did in your code sometime in the past, and then it became so slow that I had to go back and use pandas again.
Yeah, okay, very good question. I do think that, first of all, like obviously this is a generic advice, and performance optimization is very targeted, so you need to identify the place which is exactly the slowest one. And I would actually use strategy pattern to wrap this and then somehow isolate these kind of complicatedness of figuring out how to do that. So that's one technique what we use. We use a lot of number if you need to do performance coding. And any kind of hackery, hide it away behind these kind of strategy. There is a quote called wrap your difficult decisions in a class, you know, and this is exactly when you end up that I must break readability or maintainability in terms of for achieving some kind of feasible performance improvement. That's a difficult decision, and you need to isolate it and make sure that you achieve the goal what you want. But you know, these are not, you know, iron laws, you know. Please feel free to break them at any point you want.
Any other questions? No? Okay. Oh, one more.
Thank you for the talk. There are a lot of tools already in the open source community. What do you think about cookie cutter, the data science cookie cutter, in terms of clean architecture, and how can you combine it with the whole thing we had on this talk?
I would see that these are parallel things. Cookie cutter is mostly for structuring your project profile, if I remember correctly. This is more like structuring the abstract, structuring your code, you know, the product itself, and not the physical location of the files. But these are parallel to each other.
Great. Well, if no one has any more questions, yeah, we can finish for lunch. Thanks again, Laszlo.